Good afternoon. My name is Dragan Milicev, and together with my colleagues Žarko Mijailović and Srđan Luković, I'm going to present you FastOQL. This is a new Java-based tool that can help you improve the performance of your Hibernate HQL queries. In particular, the problem that FastOQL solves is the following. Sometimes, in some occasions, you have to design complex HQL queries. Complex means that the queries should span over many classes and many relationships among them, between them. Those classes take part in some inheritance hierarchies. And when you execute such queries against rather large databases, meaning databases with millions of even 100 millions of records, those queries can perform rather poorly. They can take a very long time to execute, or sometimes they can even fail to execute. FastOQL may be a solution. It is actually a Java library that improves the performance of object queries by producing more efficient, more optimized SQL queries translated from object query language. Let's see how it works. This is a motivating example. This is a very simplified excerpt from a system that we had to build a couple of years ago. That was a big national system for issuing electronic biometric ID documents like passport ID documents, driver's licenses, ID cards, etc. And there we had a kind of a conceptual model that looks like this one in a simplified way. There we had, or here we have, two kinds of entities, like legal entities, organizations or companies, and persons. Each entity can have multiple addresses. Those addresses are recorded in objects of the class address record. The address record, each address record refers to a city. Cities are organized into territorial regions and so on. Then each entity can apply for many personal identification documents. So there are many applications that can be associated to each entity, and the applications can be of different specific type, like ID card applications, passport, driver's licenses, and so on. On the other side of the system, of the conceptual model, we had a typical role-based user authorization system, meaning that the users of the system are organized or associated with roles, and each role is assigned a set of access rights, meaning that a certain role is authorized to do a certain kind of modifications or operations on a certain kind of objects in the system. And in addition, there was a territorial authorization system, meaning that each user was authorized just for a set of territorial regions. Meaning then that the user is authorized only to manage only the applications for documents of the persons, submitted by the persons or entities who have any address in that region. And now we have to build some queries. Let's start with a rather simple one. We can pose that query either to provide the results to the user interface search of the user on a web page, or to produce a kind of a report, or we can simply want to fetch for a couple of objects from the code, meaning programmatically. But anyway, here in this example, we want to fetch all applications for driving licenses submitted on a certain date that the current user is authorized to modify. So it looks like a simple query, but it spans over many classes and relationships. Here is the integral model of what we have already seen before. So in this query, we have to start from a specific kind of applications, like driver's license application. Then we have to navigate over the inheritance relationship to the base class application in order to fetch the entity, then to navigate to the address records, cities, regions, just in order to check for the authorization, whether the selected user is authorized for that region and transitively to that kind of application. And on the other end, we have the roles and access rights to check for the access rights. And here is the HQL query. So a typical HQL query that looks like the following. We select for driver's licenses. Then in the front clause, we have a couple of joins. We start from the driver license application DL. Then we navigate to the applicants, addresses, cities, regions, and so on, like it was shown on the previous slide. And in the where clause, we have a couple of typical conditions for the username, for the date of submission, and so on. And here is how Hibernate translates this HQL query to SQL. As you can see, there are many joins here, and it is rather well known that joins are one of the most influential aspects of a relational query that can affect the performance of relational database, especially when the database is very large or huge. So what is even worse here is that some of these joins are completely unnecessary. These are those red bolded ones. If you take a closer look, you will realize that these joins actually join the classes from which we do not fetch any data. So they are completely unnecessary in a sense that they do not affect the result of the query by any means. So as a result, in this translation, we have some 15 joins. As I said, some of them completely unnecessary. And we made a simple experiment. On a simple, modest developer's machine, the specifications of the machine are here at the bottom. We executed this query on a simple database, modest database with only 1 million persons, 1 million addresses, 3 million applications, 10 regions, 100 cities, so not a big one. And we got an execution time of something above 26 seconds. Of course, when the database gets larger, this time can dramatically increase, and we are going to see this later. This kind of cases is very often in practice, and Hibernate developers typically escape from this problem by switching to writing native SQL queries. But of course, if you write native SQL queries, then the work is completely different. You develop on a lower level of details, lower level of abstraction. You have to consult the Hibernate mappings. Of course, the work is much more difficult, much more tedious, and of course, the produced query is dependent on the mapping. It is more difficult, of course, to understand and to maintain. And here is how we offer a solution by FastOQL. In FastOQL, we use a slightly different dialect of object query. It is a derivative of a standard OQL, but with some little modifications, some small modifications that we are going to see later. Of course, the syntax flavor is the same as in HQL. There are some minor differences that we are going to see a little bit later. But basically, the form is the same. You have the select clause where you select for some objects and some attributes of those objects. In the from clause, we do not use the explicit join keyword. We just concatenate the navigation clauses by the comma separator, and we use the dot notation. They both assume the inner join. So you start from a driver's license application DL, then you navigate from DL to applicants, addresses, city, and so on. You split those navigations by commas when you want to introduce an alias in order to refer from the where clause. And here in the where clause is completely the same. in those two queries. So the difference is between the queries really minor. And here is how FastOQL translates this query to SQL. As you can see, the number of joins is lower, and the difference is rather obvious. As a result, FastOQL's translation to SQL has 9 joins as compared to 15 joins from Hibernate that we got from Hibernate, and the execution time drops from 26 seconds to 19 seconds. It may look like not a big difference, but let's go on with a slightly different example, with a slightly different query that looks almost the same as the previous one. Here we have a query that should fetch all the persons that have applied for a passport on a certain date and that the current user is authorized to read only. So almost the same one. The only significant difference is that here we want to select for objects of 2 specific classes instead of only 1. So we want to filter for the object of only one kind of application, passport application, and only one submitted by only one kind of entities. And the rest of the query is the same, completely the same, or basically equivalent and similar. In HQL, when you want to select for 2 specific kinds of objects, you have to use some terms like this one, where you filter for the class of the object. So in the where clause, you specify that you filter for the objects of only one specific class. And in FastOQL, we use a slightly different approach. We start from the object of one specific class, person P, then you navigate over p.applications, but you use the colon operator to downcast, to specialize the objects that are searched over this navigation to one particular subclass. So this is the difference, but the difference in the source object query. But the difference in the translation is much bigger. Here you can see the HQL's SQL. As you can see, there are a number of joins, and some of them are now outer joins, left outer joins. And these are necessary because in the where clause, Hibernate produces some case term that selects only for the objects of certain classes. Our translation to SQL is much more compact, as you can see. And as a result, to compare these two, for this example, the number of joins drops from 18 to 11, and the effect on the execution time is dramatical. For the same simple machine, developer's machine, under the same conditions, the same database, the execution time is more than 10 times different. So instead of 23 seconds that we have with FastOQL, Hibernate's translation will execute in more than 260 seconds. And we are going to see how this increases and scales to even larger data volumes. So this was the idea. This was the general approach. Now we are going to see a little more details about the object query language.
Okay, thanks, Dragan. So we have seen how FastOQL compiles object queries into efficient SQL. And before we go deeper into performance analysis and measurements, I will focus on notation and features of our query language, which is basically a dialect of a standard object query language developed by ODMG. I will also discuss the API and the restrictions one has to know before starts using FastOQL. Both in terms of syntax and semantics, our object query language is very similar to HQL. It of course supports select queries, and in fact select queries are in the focus of our query language. Queries that span over arbitrarily many classes and relationships. In the current release, we do not support left, right, and full outer joins, and we do not use join keyword in the navigation or in the from clause. Instead, we use .compact notation in the navigation clause with dots and commas, and we always assume inner joins. We also assume inheritance, which means that you are always allowed to use and address inherited attributes in every place in your query. And we also assume polymorphism, which means that when querying for objects of a general class in a class generalization hierarchy, you can expect objects of subclasses returned as well. And basically, this is of course unless you use type specialization or downcasting. We use colon operator and the type name for that, and we put them in a navigation clause. This is slightly different than which prescribes HQL, and there you have expression in the selection clause that basically do the same thing. Of course, we support results ordering and grouping and unions of two or more homogeneous select queries. We also support parameterized queries with parameters enclosed with hash signs. We also support aggregate functions and results pagination with limit and offset keywords. And one very important thing here is to be said, and that is that our query language return object IDs instead of objects. Our queries return object IDs instead of objects, and this is basically a small trade-off that allows FastOQL to perform additional optimizations. Of course, major optimizations come at no cost. And if you want to use real Java objects with FastOQL, you should basically use Hibernate load service and, of course, return object IDs from our queries. And let's see now how to use FastOQL. It comes as a jar file with small and simple Java API for execution of object queries. More precisely, it is basically, its purpose is compilation of object queries into SQL, not exactly the execution. So before you start working with FastOQL, you have to configure it. And in other words, you have to provide it with the details about the object model. And of course, object model is stored in Hibernate configuration. And regardless of whether you use annotations or XML to configure Hibernate, you configure FastOQL by calling FastOQL configure method and providing it with the Hibernate configuration object. So then you can work with object queries. You prepare your object query and you compile it with FastOQL create SQL query method with the object query and valid Hibernate session objects. For parameterized queries, you can use setParameter method. And for execution of queries, you should use Hibernate and execute FastOQL generated SQL queries just like any other SQL query. And finally, a few words about restrictions. As we already said, we do not support left, right, and full outer joins, but This is, of course, planned for future versions. And we also do not support shared primary key for one-to-one associations, no multi-valued attributes, no enumerations yet. FastOQL currently compiles object queries for Oracle, MySQL Server, SQL Server, and PostgreSQL databases, and more is on the way. So now let's see where we are in terms of performance. Sergeant will explain that.
Okay. Okay, let's now see how much FastOQL can influence performance. As we said, FastOQL improves performance by omitting unnecessary joins, and that's most noticeable when we have inheritance and association tables. We have performed comprehensive benchmark for these cases, and the benchmark model is shown here. Please note that the benchmark model is of variable size, so we can have up to 5 classes in inheritance hierarchies, and relationships can span over up to 10 classes, named A1 to A10 and E1 to E10. Classes are simple. There is only one integer and one textual attribute, and the ID is not shown here. We have performed benchmark for all different model sizes. Inheritance are mapped using table per subclass strategy, and associations are mapped with many-to-many collections. Each object is linked with one random object via each association, so only one. And we performed benchmark for different database sizes. We started with 1,000 objects, 10,000 and up to 10 million objects. And the total number of records in the database is almost 8 times the number of objects. We ran approximately 1,000 queries for different model sizes, and queries were in this form: select count from X1. And then we can have up to 9 joins, depending on the model width. Where clause is optional, and in where clause we can have variable number of conditions, 0 to model width. Of course, we can have either integer or text attributes in the model, in the conditions. Okay, let's see now about results. Here, first we can see the number of joins compared. On the horizontal axis is shown model dimensions, model depth and model width. And on the vertical axis you can see the join count. Obviously, in simple cases, number of joins is comparable, but as the model grows, FastOQL generates SQL queries with far less joins. In worst case, HQL generated SQL query with almost 70 joins, which, for example, MySQL doesn't even accept. On this slide, we can see execution times compared. The model width and model depth are plotted on the horizontal axis again, and on vertical axis is execution time in milliseconds. Both diagrams are scaled the same way. So FastOQL times grow almost linearly with model size, but you cannot see this on this slide because in case of Hibernate, when the model grows after 15 or 20 classes, times rapidly start to grow. This is another perspective. Execution times on the horizontal axis is now shown the number of objects, and as you can see, as the number of objects grow, so are the execution times. But again, FastOQL scales much better.
Okay. This was just a small extraction from our benchmark. It was, as Srđan said, a comprehensive benchmark. You are welcome to visit our website, FastOQL.com. That was established just recently. And there you can find more details about everything. You can find more details about the benchmark itself. So all the very details of the benchmark are open and presented so that it can be verified by a third independent party. So all the details about the assumptions, preconditions, everything, you can find the source, the results, and so on. Of course, you can find complete documentation for FastOQL, although it is rather simple to use, as you have seen. And most interestingly, you can download a free beta version so that you can try it yourself. Your questions are welcome. Now we are, of course, open for questions over emails. Here are our email addresses. Thank you very much. And now, if you have any questions, please go ahead. Yes, please.
Did you try the benchmark test with another mapping strategy than the class, than stable for subclass?
The question was, have we done any benchmark with another mapping than the one mentioned here? I will say that it's not about the benchmark, it's about the strategy. We are focused on only this mapping, at least for the moment, due to several reasons. First, FastOQL is actually a derived technology from another technology of our company, and this is Soloist, a model-driven development tool for business applications using executable UML. And actually, what we did is that we extracted, there we have our own persistence layer and object-to-relational layer and query language. So we just extracted this one from there, and we designed this particular tool. This was one reason. But another more important reason is that we somehow feel that this mapping is most commonly used in practice. At least it is, as far as we know and as far as we have read via blogs, comments, etc., and documentation, even the Hibernate's documentation, that this one is mostly recommended. So we were focusing on only this particular mapping. Maybe in the future, and we'll support the other ones. And the third reason is related to the previous one, because we feel the most dramatical improvements not for all cases, but only for some cases, some of which we have already emphasized here. So especially when you have inheritance hierarchies, where different classes are mapped into different tables, and where you have association tables for many-to-many relationships. These are especially critical points where we can improve, because, as I said, Hibernate simply produces joins where they are not necessary. So it was a rather longer answer, but I have revealed the entire story behind that. So there are a couple of reasons why we do not support other mappings for the moment. Thank you. Other questions we have? Thank you very much. Thank you for your attention. It was nice to